Okay, so since we just came back from lunch, I'll give the key takeaways, but you guys are still awake. So as I said, so we're going to talk about non-equilibrium thermodynamics of black hole coronae. So one of the most important ideas that we have to think about is that variability, and in this case, extra variability, is really important because this gives us information that is just beyond any sort of time average coronal physics that we can have. So based on this idea, the variability is so important. So we're developing this model that is based on non-equilibrium thermodynamics that is going to try to explain coronal variability, and we're inspired by the Kappa mechanism for pulsating stars. And the third takeaway that is based on the work that we're doing, so our model, as we're going to see, is based on coronal self-oscillations that can drive this extra variability, for example, like QPOs. And we'll see how all of this also links to possibly generating turbulence in the corona or powering the jet. Okay, so for the outline, so at the beginning, I'm going to talk about the observational motivation, and in this case, it's variability and QPOs. Then we're going to go into how we're going to incorporate these picture of variability into non-equilibrium thermodynamics. And especially, it's very important for us, especially theorists, to think, like beyond equilibrium. And now we're going to be using these tools for non-equilibrium thermodynamics. And we'll see how self-oscillations come into play. And then at the end, we'll all link it for how it's going to be implemented in the black hole coronae. And in this case, I'm going to be talking specifically about extra binaries, but it also can be applied for AGNs. Okay, so this is the observational motivation behind the work. So we're going to be talking about QPOs. So QPOs are these quasi-periodic oscillations. And we identify QPOs by performing the power spectra of the time series of X-rays. So we'll see these nice quasi-periodic signal in the flux. And QPOs are, they have different categories. But for us today, the most important is that we have these high frequencies and low frequency QPOs. So here we're going to be talking mostly about low frequency QPOs. And one of the important things and why it's for us it's nice to use it is because these are detected in the hard band emission. So we know that their origin, or at least their expression, has to be related to the corona. So therefore, we can use it as diagnostics to get some information of the fundamental physics that is happening near the black hole. Okay, so this is the observational motivation. So now from that, how do we go to non-equilibrium thermodynamics, and how do we incorporate it into the physics picture that we want to get to? So the piece of physics that I'm introducing here is the concept of self-oscillations. And the nice things about self-oscillations is that they can generate and they can also maintain the periodic motion by a source of power that doesn't have that periodicity. So it's intrinsically different from something that we know, for example, like resonance systems, where we have, like, for example, stuff that we really know, like force or parametric resonators, where the source of power has that periodicity, and then it just puts it into the system itself. But here, the nice thing for self-oscillations is that you have the source of power. That source of power doesn't need to have a periodicity. So the system will take that power, and then it will drive these oscillations. So that's the key part. And this is a phenomena that has been observed in different systems. For example, like I put some pictures here of neurons. And if you guys know about the Tacoma Bridge, so that was also a self-oscillation. But in the case of astronomy, we have pulsating stars, and pulsating stars, we have them that they have this kappa mechanism that is the one that we're going to be basing our ideas on. So just to summarize, so remember that self-oscillations, they can generate, and very important, maintain an oscillation, but the source of power doesn't have to have that periodicity, okay? So this sounds too nice, right? It's a really beautiful piece of physics, but we need to put it into the context where you have some requirements so that we can actually have it in the corona. So these are the 3 requirements for self-oscillations. So the first one is that you need a disequilibrium that in this case is going to be thermal. So the system has to get to at least 2 different temperatures. So think cold and hot. The second requirement is that we need something that is a macroscopic mechanical degree of freedom that is going to be linked to our system. So think about it like if you had like a piston that is going up and down, that'll be the mechanical degree of freedom. And the last one, and the last one is the tricky one, and this is where the physics and the interesting dynamics come from, is the fulfillment of these radiating criterion. So now let's take a look at how we can start thinking about the criterion, especially how it comes to work when we were thinking about the black hole corona. Okay, so this is the criterion, and let me give you some idea on how it actually works and how the different components come to be. So here we have that this W represents the work. So this is the work done by the system. And this quantity here, it has to be positive so that we can fulfill the criterion. So this delta Q is the heat that is being absorbed from the surroundings, so the heat that comes in to the system. And this TD here is the temperature difference. So the temperature difference between the instantaneous temperature and the mean value. So this TD is positive when we're at a temperature that is higher than the average, and is negative when we're at a temperature that's lower than the average. So what does the criterion tell us? Since we need these to be positive, so this has to be positive, and this has to be positive, or this has to be negative, and this has to be negative. So that's telling you some idea on how the heating or how the cooling is going to come to work in your model. So if we were modeling the heating, so the criterion would read like this. So we need the temperature to be at the highest when you are absorbing the most heat, and when you're dealing with the cooling, so you need this negative and this negative. So we need the system to be at its coldest when you are rejecting the most heat, when you're emitting the most heat. So what we're doing here is that we're going to be modeling the cooling. So the criterion that we're looking for is that when the system is at its coldest is when it's emitting the most heat. And this is why it's a little bit counterintuitive, right? Because you think that normal things do the opposite. So just keep in mind that that's the guidance that we're looking for. To have the system, have the corona to be at the coldest when we're rejecting the most heat. Okay, so how does this come together? So since we're talking about thermodynamics, so we know that heat has to come in, and then heat has to come out, and then you have to do some work, right? So this is why I'm calling this the coronal engine. And it's just because you are dealing with these different components. So let's take a look at how they start to work. So here we have that heat is introduced in the system. So you have some Q in. Again, as I said, so we're modeling the cooling. So the heat is we're just assuming that it's constant. Then you have some Q out that is, in this case, is going to be the observed luminosity. In this case, will be the X-ray luminosity we observe. And here is the interesting part, right? Because we need some work to drive the oscillation. So this heat that comes in is going to be used to do some work. So the main one that we want to have is some work that is related to the oscillation. Then we're also going to have some magnetic work. And if you had the engine just like that, these just Q in, this type of work, and then out, this will give you like an infinite amplitude. So it's just going to be producing and producing some work. But we needed to have a limit cycle, something that would actually limit our engine. And this is why I'm introducing this work extraction that is going to be limiting the work that the engine is going to do. And the work extraction is very, very important and very interesting because we can, it's not heat, but it's actually work. So we can put it, to actually do some work, right? So this is why we can use it to, for example, generate turbulence, or to also drive something like a jet. So this is the main idea. We have some energy comes in, then the Q out is going to be the observed luminosity. We put it to work to drive the oscillations, but you can also have some work extraction that's going to be for the turbulence. Okay, so now that we have this concept of, we're looking for something for QPOs, for availability, then we have self-oscillations, and then we have these components. So how do they come together in the corona. Okay. Okay, so this is the cycle that we have for the corona, and again, remember that we're looking for this condition here for the criterion, right? Lower temperature, and this is when you have the most heat extraction or the most luminosity. Okay, so the setup for the corona is the following, right? So we have the disk, we have soft photons coming from the disk, and we have a corona that has hot electrons, and we have some observed luminosity. So the first stage in the cycle is that these soft photons are going to be undergoing like inverse Compton here. So we're going to have a production of hard photons. And then the overall temperature is going to be lower, right? Because the electrons have to share their energy with the hard photons. Then the next stage, there are going to be some hard photons that are going to be having like enough energy to pair produce. So now we have a population of electrons here. We have a population of pairs, so the charge density has increased, and the overall temperature of the system is going to be lower, right? Because now we have a lot more species that are sharing the energy, and the peak of the cycle, and this is where we fulfill our requirement, is that here we're going to have the lowest temperature because, the lowest temperature because we have these pairs that are going to be here stealing the energy from the electrons. We have also a population of sub-threshold photons that are not able to pair produce. But once we have these conditions here, so the charge density has gone in higher, so we have more particles in the corona. The optical depth is going to be higher. Because of that, so we're going to have that the soft photons are going to be having an easier time to steal energy. So inverse Compton is going to be more effective. And because of that, then we're going to have a maximum luminosity. And this is exactly what we wanted, the lowest temperature and maximum luminosity. And this is where we fulfill our requirement for self-oscillations. And because it's a cycle, then we have to go back, right? So these pairs are going to recombine. They're going to annihilate in the system and then deposit in further energy back into the corona. And as I said, we're modeling the cooling, so we assume that the heating is constant, and then we go back to the initial point, and then so on and so forth. Okay, and this will go on as long as we're able to have some energy to pair produce, which is the most important one. Okay, so just to finish, so now we have seen these, how the QPOs can be related to these very interesting piece of physics that there is self-oscillations that is, that is also present in, for example, pulsating stars. And hopefully with these, we have this idea that variability is really important when we're probing the dynamic physics of the corona. And this is why exactly we're introducing non-equilibrium thermodynamics, because there's a lot of rich information that will be missing if we're just having equilibrium dynamics. And especially when we introduce coronal self-oscillations, then we know that it's possible to have in the corona, or at least we have the conditions for that. And it's also nice because we can use this model to link different things, for example, QPOs, turbulence, and jets. And so since we are at the AXIS conference, so it's for AXIS, and this work is going to be nice to have new sources. We're also going to have, like possibly some transient behavior. One thing that I'm really interested in is in the multi-messenger connection. So for example, you have non-thermal components, let's say like cosmic rays, neutrinos, what can we say about the conditions of the corona? And especially now that you guys are going to be in a different orbit, so we're also going to have a longer ways to like look at, for example, like AGN. So we have more information on this sort of behavior. Right, thank you so much, and I'll take some questions.
Questions for Vanessa?
Hi, Vanessa. Can you go back to the cycle that you were showing? So is the QPO varying? The QPO timescale is the timescale of this cycle.
Yes,
Okay.
yes. So we'll see. So the maximum luminosity that you see in the QPO will be related to the maximum luminosity there. Yeah.
Okay. And then where in this schematic?
Where
in this schematic is the connection to the jet? I understood you need to take.
Yeah. So the jet is something that I'm thinking right now, because since we need the cycle to be limited, right? So
Yeah.
we know that we observe a cycle that is not, we observe like QPO that doesn't have infinite amplitude, right?
Yeah.
So since we know that we have to have a limited cycle, so there is something that there are things that are going to be against the work that has been done by the engine, right? By the Corona. So you have two different things. So once you can have regular dissipation, so like Landau damping or something like that, very, very simple. But when we introduce these work extraction, when I'm calling work extraction, and I call it work extraction because it's like you're taking work from the engine. And the way that I see it is like imagine if you have like a car and then you have the engine of the car, and then you know that your car cannot go to like infinite speed because you have drag, right? In the case of the Corona, the drag will be this work extraction. So this is energy that is not heat, but it's energy that can be used to do something. And
so
this
it should also be periodic?
Huh?
It should also be periodic?
Not necessarily has to be periodic, but it could be periodic as well. Yeah, yeah. But like, yeah, because in the case of this work extraction, it's you wanted to go, yeah, you wanted to go with, so the regular work goes with like the velocity. So this one has to go in phase with that. Not necessarily exactly in phase, but mostly in phase. So at least like 45 degrees or so. Like, yeah, but it's true. It has to go with the same phase, so that, because if it doesn't go with the same phase, then it doesn't do its work, right? To counteract the work that has been done, right? If it will go in the same, like in another type of phase, it wouldn't do what I wanted to do. That is actually extracting work. Yeah.
Okay, we have time for one quick more question.
Yeah.
Thank you for the talk. So this is one of a number of models for QPOs and, well, of course, a QPO. Does it have any unique or observational predictions or things that you can test to try and demonstrate that it is or isn't the mechanism?
Yeah, so one of the most simple things that we can do here is that, for example, we have a specific threshold, or like when we have the conditions for the cycle to happen. So we can say when it can stop and when it can turn on, because all of these depends on pair production, right? So if you don't have enough energy to pair produce, then this turns off. And this is why it's important. And another thing, I didn't have enough time, but like another thing that is nice, and perhaps we can talk about it later, is this non-thermal component, because since we depend on this non-thermal component to drive the oscillations, so you can assume that if you turn it off, what will happen? So this is why it's nice to think about the non-thermal component. Yeah.
Okay. We're running out of time. So Thank you, Vanessa, again.
Thank you, Javier.
Next, we have Zhao, and he's going to talk about AXIS and Nexus synergy. Nexus, is it? Yeah. And I signal you when you have to work.
Turns it on the screen, so you don't have to turn it on.
See it on conference.
So thank you so much. I mean, it's really a great pleasure to see all the experts in this room, and really nice to be in this, beautiful place. And today I'm going to talk about AXIS-NEXUS, one field for both supermassive evolution and also the time domain study. So this work is a great effort of a huge collaboration from Nexus collaboration, the PIs, the USN from UIUC, and also a lot of people, and also Nico and Stefano here. So what is Nexus? Nexus is the North Ecliptic Pole Actual Galactic Unified Survey. So it's a JWST multi-cycle, 3 years, 368 hours, GO, spectroscopy, and also imaging survey. So in the next 3 years, we will have continuous cadenced spectroscopy and imaging monitoring of this field. And the field has, the survey has 2 tiers. The white tier includes a 400 square arc minute survey, and it will be performed by the near-time WFSS. So all the source in the near infrared from 2.4 to 5 micron and doing spectroscopy. So all the sources in the field will have spectroscopy and image in the same time. And the deep tier includes a 50 square arc minute monitoring and doing with the near spec 0.6 to 5 micron spectroscopy and also imaging. So what it will give us is a first spectroscopy redshift and classification complete survey. So all the emission line galaxies, for example, the AGN or galaxies, star-forming galaxies at magnitude below 24 in the 444 band, will have reliable spectroscopy in the whole 400 square arc minute. So this figure tells us about the sensitivity of the wide tier here of the 400 square arc minute, and also this is a simulation of a redshift to quasar. And you can see that we can measure very reliable the redshift, and also if they are broadline, we can measure the black hole mass. And in the deep survey, that's the central 50 square arc minute, we will have 30 magnitude threshold that all the sources above 30 magnitude will have a spectroscopy, and the deep survey is here. And also we have a Euclid deep field in this centered at this nexus field. So we will also have an optical spectroscopy from Euclid. So what it tells us is that a nexus will provide currently the largest galaxy sample with spectroscopy redshift measurement. So the right figure is the different JWST extragalactic survey has been performed, and the x-axis is the sensitivity of different surveys, and y-axis is the number of good spectroscopy redshift of sources. So you can see the nexus deep field is here. So it provides currently the most number of spectroscopy redshift sources, and also the Y field is here. And so what we can use this spectroscopy information to do supermassive black hole evolution. For example, here I show a simulation of what a Chandra 1 million seconds observation of the field can measure the number density of the AGN as a function of redshift in different X-ray luminosity beams. For example, the red is the Cepheid-like galaxy from 10 to the 42 to 43, and then 43 to 44, and the bright one from 44 to 45. So after combining all the 1 million seconds, we will detect 300 AGN. And this is the constraints we can have on the number density. However, if we have AXIS, which has a much better effective area, a flat PSF, and also a much larger field of view. So one axis pointing can cover the entire field, while Chandra needs 5 pointings. So with 1 million seconds axis observation, we can constrain all the different luminosity AGN up to redshift 7 of their number density, and we can detect 1800 AGN in only in just 1 million seconds. And more interestingly, we can also detect a lot of faint or low luminosity AGN below 10 to the 22, 10 to the 42. So why this is important? Because 23% to 59% of the X-ray detections in the previous extragalactic surveys, they do not have reliable spectroscopy. And those sources without spectral Z, they are most important because they are either faint, they are, or like heavily obscured, and or they're just can tell us about the population synthesis model. They are important ingredients. So what JWST is going to survey this, how JWST will going to survey this field. So starting this June, so next month, JWST will monitor this field every 2 months. So just starting next month. And what time domain study can be performed with, using the synergy between JWST and AXIS. So JWST will survey the deep field every 2 months for 3 years, and wide field every year for 3 years. And the Nexus field is also in the ultra deep Euclid field. So it's in this field, Euclid will survey 16 times deeper than the normal other fields. And it's also in the continuous viewing zone for other telescope like Sphere-X, which launched 2 months ago, and the NEAR survey, which the next generation WISE, and also UY Pan stars and on-ground telescopes. So here we propose to do a 1 million seconds axis survey of the Nexus field taken in 50 epochs. Each epoch has 20 kiloseconds in 5 years. So this allows us to study, to sample the variability of the sources from days, weeks, months to years. So we will not do a month cadence, but we sample different intervals, time intervals, to study the different significant variable sources. For example, short gamma rays in like 10 kiloseconds or kiloseconds level. So we study them in intravariability. But for AGN, TDE, or other galactic sources, or like supernova, we study them at different time scale. So this figure shows you the peak luminosity of those sources, of those significant variable sources, as a function of the rise frame time that's above the half of their peak luminosity. So we need almost 3 years rise frame observation time to measure as many sources as we can. So to conclude, we hope we can persuade you that in this one single field, we can do both supermassive black hole evolution and time domain study. And thank you.
Well, we have plenty of time for questions. Can I ask you, while people get ready for formulating their own questions, can I ask you, it's not super clear to me what's the status of this survey with JWST. Is this already ongoing? Will happen? Or is this an approved program?
Yeah, this is approved last September. So it will start this year from June for 3 years.
For 3 years.
So every 2 months, the cadence is.
And the Euclid
Euclid is already.
It's already ongoing, right?
Yeah, so Euclid survey this field for, every month.
Okay.
So yeah, so they almost overlap and have really high cadence.
So there is overlapping in time, and like there is a simultaneously.
Yeah. Almost. Yeah.
Okay. Any other? Okay, sorry. I didn't see who raised the hand first.
Yeah, so just given your solid angle and your depth and sampling and so on, have you made estimates as to how many extragalactic transients of various types you might expect to detect in terms of, say, TDEs or off-axis gamma ray bursts or whatever? I didn't see any numbers, but perhaps I missed something.
Yeah, this is a good question, and I think that's what we want to explore with, for example, a Chandra program on the Nexus field.
Sure, absolutely. But I presume, in order to win the time, you had to make some projection as to how many things you might expect of various types.
Yeah. I will not have a concrete number, but I would say that maybe at least not at least 1 TD in the 5 years.
Okay.
Yeah, at least
fine.
one.
And
TD.
have you tabulated how like other types of transients as well?
Yeah,
Off
other, for
axis
example, some
CRVs.
very interesting AGN flyer. I mean, that's maybe even 1 per year at least. And also, I mean, you see a continuum variability AGN, that's normal. I mean, that's not super interesting.
Right.
But if you see line transient, that will be super interesting.
Okay.
Yeah.
Thanks for this. I'm just curious. You mentioned before that in previous X-ray surveys, most of the X-ray AGN don't have spectroscopic redshifts. And I'm wondering if you were to do 1 megasecond with AXIS and get 1800 AGN, just in terms of what we would expect to see with the optical or near-infrared magnitudes of those counterparts, do you have a sense of how complete you would get in terms of how many of those sources you would expect to already have redshifts in the Nexus survey?
Yeah, that's a good question. The reason we use 1 milliseconds is that we want to match the JWST sensitivity. So that is the 24 magnitude here. Yeah, for most of them. And because JWST do the infrared rest frame, maybe I mean the observer frame infrared observation. So even for the type 2 agent, obscured agent, we expect that they have emission lines.
All right, just to follow up on that question, which is a good one. I'm not familiar enough with this particular filter, but like, what does that correspond to in terms of an R-band magnitude?
So 24 means almost 10 to the minus 17 erg or 16.5 ergs per second per centimeter.
So you're going down to like what R-band mag?
Sorry?
For a typical SED, what sort of R-band magnitude are you getting?
R-band.
Yeah, R-band, yeah.
Oh, I mean, this is difficult to say because, you know, it depends on obscured or unobscured. But for unobscured agent, I think it's about R-band about 25.5.
Okay.
20, almost 26.
Okay, fine. That's good. I mean, of course, there are a considerable number of AGNs in the Chandra deep fields that are fainter than that in R band.
Yeah.
So, you know, you could look at, you know, some of our old papers by Luo et al., where we give those magnitude distributions to answer that type of a question.
Yeah, thank you. Yeah, we use the Cosmos result to do this kind of estimation. Oh, yeah, definitely.
One, probably the last one.
So as a member of the SphereX science team, we just started our all-sky survey on May 2nd. I'd be very curious to know when we're going to hit your field and when you're going to hit your field, what the cadence is going to be like. We hit a patch of sky every 6 months unless it's near the ecliptic poles. So I'll go back to the team. I'll mention your upcoming survey.
Okay, thank you so much. Sorry, which team are you from?
SphereX.
Oh, thank you. Yeah, thank you so much.
I think we have something to talk about, yes.
Yeah, we really look forward to SphereX.
Yes, we're only going to go down Z about 3 or so we're not going to go really deep. And about K magnitude of 19.5.
Yeah, but still, I mean, you have a really good spectrum.
We'll have the whole sky, yeah. We'll be talking.
All right, thank you, Xiurui. And I've been told that Sophia is not here, so we'll move to Robert Stein. Over here, yeah. And Robert will be talking about exploring the synergy between high energy neutrinos and X-rays with AXIS.
Okay, great.
Okay, thanks everyone. Now time for something a little bit different. So I'm Robert Stein, I'm a postdoc at UMD, and I'm going to be talking on behalf of a larger group of people on the topic of neutrinos with AXIS. And since I think I'm a little outnumbered as a neutrino enthusiast, let me just start by reminding everyone what neutrinos are and why they might be interesting. So we have known for over 100 years that the Earth is continuously bombarded by charged particles known as cosmic rays. And what we know now is that these particles can have extremely high energies, far beyond what we could ever reach with a terrestrial accelerator here on Earth. So you're talking EeV energies or above. And obviously, as astronomers, it would be great to understand the really extreme astrophysical processes which must surely be required to produce such high energy particles. And the problem is that because cosmic rays are charged particles, they are deflected by magnetic fields. The universe is full of magnetic fields, and therefore it's actually very difficult to work out where these cosmic rays are actually coming from. So if you have a cosmic ray illustrated here in red, it will follow a windy, bendy, curvy path, and by the time it reaches the Earth, even if you detect it perfectly and you reconstruct it perfectly, you say this particle came from exactly over there on the sky, it doesn't really tell you very much because the actual source of the cosmic ray might be way over there instead. But fortunately, nowadays, we live in the era of multi-messenger astronomy, and the messenger that I am most excited about is the neutrino. So neutrinos are electrically neutral, which means they travel in straight lines, and they only interact via the weak force and not very much, which means they can travel directly through matter, through dust, even through the Earth itself, which is great because it means that they can carry this information to us from the very distant cosmic accelerators all the way here to Earth. And we nowadays have a network, an ever-growing network of neutrino observatories which detect these neutrinos and can reconstruct them on the sky to a precision of about a degree or less. It's getting better all the time. And what that means is that these things are not just neutrino detectors, but they're really neutrino telescopes. So you're really detecting particles from space and able to work out roughly where they're coming from. So where do neutrinos come from? Where are these astrophysical accelerators that we are also interested in? And I would say that at the moment we have some answers, but many, many open questions. So what we know is that some neutrinos do come from our own galaxy, which makes sense because some photons also come from our own galaxy. But most neutrinos seem to be extragalactic. And then in terms of where those extragalactic neutrinos are actually coming from, we know that some come from the nearby active galaxy NGC 1068. We know that flaring blazars produce some as well, especially TXS0506. And we have some evidence also that tidal disruption events contribute to this flux. But I want to really emphasize there is a large number of neutrinos that are detected, and most of the time we really have no idea where the neutrinos come from. So there's a lot that's really not known at all. And this neutrino flux, as we're learning just in the last couple of months, extends up to at least 100 PeV. So really very, very extreme energies. Why would you maybe be interested in neutrinos in general? So since I'm nominally in the AGN session, let me talk about an AGN. So this is, as you see on the left, NGC 1068. And this is the hottest source in the neutrino sky. And so I have a figure. This is one of the only real figures I have in my talk. So let's walk it through a little more carefully. What you have on the x-axis, you have energy. On the y-axis, you have flux. In green, you have observations of this source in gamma rays. And you can see that it has a spectrum which is falling over time, and then suddenly these become upper limits. And beyond that, we really don't know very much. And then if you look at the very dark blue navy line, there is a straight line with a shaded butterfly region accompanying it. That is the source as measured in neutrinos. And if you just take a step back and look at this, what you're saying is that you're detecting a source. It is over 100 times brighter in these measured particles than it appears to be if you just look in photons on their own. And the thing is, neutrinos cannot be produced in isolation. If you're producing neutrinos, you're also producing photons as well. So within the center of the source, the photon spectrum will look very much like this neutrino spectrum. But between the inside of the source and the photons trying to escape and actually making it to Earth, basically all of them get absorbed and we don't measure any photons at all at this high energy. And that's really what neutrinos allow you to do. They provide this absolutely unique window into the most extreme astrophysical processes that go on. We've been hearing a lot about how difficult it is to model AGN. If only you had a way to look right into the center and see what the intrinsic spectrum was, that's what neutrinos offer you. And as I said, it can be really wildly different to what you would see if you just looked in photons. So then I want to answer the question, why am I here? Why would you be interested in neutrinos and also in X-rays together? And the thing to say is that neutrinos are produced in a sort of, it's almost like a particle physics experiment. Basically what you need to do, you need to accelerate particles, you need to collide the particles with something. So you need either matter or photons. And the thing is that when you produce neutrinos through photon interactions, you're exploiting a resonance, which means that the photon have to have a very specific energy. And so for the neutrino detectors that we have that measure to TeV, PeV energies, you require specifically X-ray photons. And so, of course, it's really natural to think that if you wanted to find neutrino sources, you would look in X-rays, because if a source is already detected in X-rays, half the battle is already won. You already know that it has enough target to potentially be producing neutrinos. And it's also worth noting that all of the neutrino sources that we have so far have been measured in X-rays. And again, that's really no surprise. If you just think of the physics, it really makes a lot of sense. So what would we like to do with AXIS, and how could AXIS contribute to neutrino science? Well, what we would like to do is to directly do tiled follow-up of neutrino localization. So there are already neutrino telescopes that detect neutrinos and localize them to under 1 square degree. There are many more telescopes coming online by the time AXIS is launched. And so it is completely feasible for AXIS to tile an entire neutrino localization region with maybe only 2, 3, or 4 pointings. So what we imagine is doing something like this. This is an illustration from when Swift does follow-up, but with AXIS's field of view and also with the better localizations and depth, AXIS is really the perfect instrument to do this. So it leverages AXIS's sensitivity and field of view. And we'd like to basically tile these neutrinos as they come in. IceCube and other observatories report them automatically in real time, very well localized, and just basically see what's there in the X-rays. And what we would imagine doing specifically is, once we have this data, we would cross-match to known catalogs. So we'd look at Eurosita, see what was there in the X-rays. We'd look at what Rubin is seeing. We'd look at radio catalogs, et cetera. And we just try and identify any transient or flaring sources in the field of view. And then what we would try and do is sort of group these by spectrum, by cross-match information and contextual information to try and work out roughly what these things might be and report them to the community. And in that way, AXIS can really be an anchor for multi-messenger follow-up across the electromagnetic spectrum, because other people are also looking at these. What we see would be very important for what other wavelengths would also see. So what might we be looking for? If you're doing follow-up in real time, you're caring about time-varying sources, and these are the main ones that would have potentially X-ray emissions. You have gamma-ray bursts, you have supernova with choke jets, you have supernova with circumstellar material interaction, you have AGN, of course, including blazars, you have tidal disruption events, and you also have luminous blue optical transients. So these are the main 6 source categories that would be targeted by our program. And so how good could AXIS do this, this experiment? So what I've done here is I've stolen a very nice plot from the AXIS TDAM Science Working Group white paper from 2023. And so this was a visualization of how well AXIS could do in 10 kiloseconds. What we're proposing for each individual pointing is 1 kilosecond, but I think it really nicely captures what we're trying to do here. So what we would actually like to do is a sort of mini time domain astronomy survey. So we take a view, and then we basically see what is there and try and work out what each thing is. And so if you look at the individual source classes that I mentioned before, if you have a gamma ray burst, they have a typical luminosity of, I don't know, 10 to the 48 ergs per second. So you can see them up to redshift of a lot, like 10 or even beyond. If you think of flaring blazars, for example, you can see them up to redshift 1, even in 1 kilosecond. For tidal disruption events, you can imagine easily seeing them up to redshift 0.3 or beyond. And even for something like AT2018 Cal, a luminous fast blue optical transient, you can see them up to redshift of 0.2. So this is really quite a lot of depth. Obviously, depending on the source class, our horizon is different, but you can really make very strong statements if you just do this a handful of times. If you have a small number of follow-up campaigns that you do, you can really start to make very strong statements about how much neutrinos could be coming from each of these populations. So just to conclude, I'd like you to imagine one thing that we might be able to find. So it's hard to imagine what's going to happen even tomorrow or next week, but let's imagine it's 10 years in the future, and AXIS is successfully launched, it's working, everything is going well. And then a future neutrino observatory, let's pick P1 at random, has detected a high-energy neutrino. And because many neutrino observatories are going to be located in water, they have very good precision. So it says there's a neutrino that is within 0.4 square degrees, and it reports that within 60 seconds. This is very normal. This is already what neutrino observatories are able to do. And then we have an automated listener that basically sees these neutrino GCNs and decides whether to trigger or not. It meets all our criteria. We submit a tiling. We do this in 3 or 4 pointings. We get observations, let's say, within an hour, and we see exactly 1 new point source, which obviously gets us very excited. We want to know what this is. And at the same time, we report that we found a candidate. And a GRB monitor reports that it has found a very low significance gamma ray burst that was detected at the same time as the neutrino. And this is actually a GRB afterglow, for example. And this would be AXIS able to localize the position of the afterglow where the GRB monitor or the neutrino itself wouldn't be able to do it. And of course, AXIS doesn't operate in isolation. Rubin, for example, wants to operate a neutrino follow-up program as well. So Rubin would be sensitive to the optical component of the afterglow. So Rubin might detect a very red source at the same position as the afterglow in X-rays and at the same position as the neutrino. And this is just the beginning. Obviously, then we would try and get as many observations as we could to really understand the physics that's going on. And between AXIS and other multi-wavelength observations, we'd really be able to fully characterize this very exciting GRB. And so here's an example of sort of the various structures that you can see in gamma ray burst light curves, just to say it's not enough to just say, oh, we found something, now we give up, but actually you really want to be able to follow this thing as it fades over time, because they really have a lot of variation in structure, and they can really tell you a lot about the physics inside. So I realized this was kind of a simplified explanation. There's many different things that we could find, but in each case, I think AXIS would be really crucial. It's going to give us the best X-ray view of these multi-messenger sources. So let me just sum up. Neutrinos are very powerful messengers, and we don't know where most of them come from, which is really great because it means there's a huge number of open questions that we really have a chance of answering. X-rays are extremely critical as a messenger because they are the target for neutrino production. So when you already detect something in X-rays, you're halfway there. Follow-up with telescopes works. It has worked before, and it will continue to do so. It's a really great tool to learn new things. And AXIS has exactly the right capabilities matched with the future neutrino observatories to really do this study and understand where these neutrinos are coming from. And it's extremely broad. I didn't mention all of the many, many observatories that are doing follow-up. Rubin's just one of them. But this is going to be a really nice sort of network that exists in the next decade that AXIS could be at the center of. So if any of this sounds interesting to you, please reach out. We're very happy to have collaborators on this case. We want it to be as big as possible. So thank you very much. Were there any questions?
Thank you, Robert. Any questions? I'll remind the people that there are other, also two other microphones you can walk to. I don't mind.
I would have been happy to do that. Yeah, so there are, of course, a number of multi-messenger network groups already working. I know at Penn State, where I happen to work, we have AMON, and there are a variety of other ones that people have set up. Would you envision plugging into one of those, or are you going to build a new one from scratch? And if so, why?
No, because I'm not stupid. Why would I?
Yeah.
As you say, infrastructure exists, and we want to work with the community. I mean, I also personally, I work on other instruments as well, doing neutrino follow-up. There's an infrastructure that's growing and developing. AXIS should be doing as little as possible. As much should be done through things like AMON, through brokers. I completely agree with the spirit of your question.
Chris. Thanks. So in your last worked example, where I agree, I think we could tile part of the sky very quickly and get down to the sensitivities to find the counterpart. However, it may typically be in a part of the sky that AXIS has never looked at before. So the sort of underlying ground truth of the sources, the pre-transient sources, might not exist. So on what time scale would you expect relevant sources to be evolving so you can recognize them, as you're looking, or would it be okay to then go back after the fact? And I mean, at what point do you need immediate recognition and localization of the source you have? Could this be done after the fact by comparing to a post-transient?
Yeah, that's a great question. So I sort of glossed over it here. I just said we will identify transient and flaring sources. Obviously, that's actually very non-trivial. I think this is probably going to be quite similar to what you're going to want to do in general with all AXIS science in terms of doing time domain astronomy science. So what I imagine, for example, is that you look at all the sources that you've detected in general, and you look at E rho zeta, you see what was already there in the field. So you see if anything is particularly bright compared to there, or it wasn't there at all. You look at things like Rubin, for example, like if you have an X-ray source, even if you're not sure if it's transient or not, but you see in Rubin there is a transient optical flare, probably the thing is also transient, and they might be associated. So I think this will definitely take some time to work out. It's not going to be as simple as this, but I also think it's very doable. Like I think even with one epoch, I think you can reliably group things into likely transients, we're not sure, likely variables.
Okay, great, thanks.
Just a quick naive question. How often do you have neutrino detections currently with current facilities?
Yeah, that's a good question. So right now, there is only the IceCube Neutrino Observatory. It detects one alert every, let's say, 2 weeks. However, in terms of like high quality ones, maybe more like one a month. But we expect like the number of alerts to really grow by the time AXIS comes online. So there'll be another multiple observatories of the same scale, and IceCube itself might get bigger. So between them, there will be plenty of alerts. We're not planning on triggering crazy numbers, but like maybe 1 or 2 a month. That's kind of what we'd envisage.
Thank you.
Thanks.
Any final questions? Right.
Thank you. So just like to get to the idea that Erin said at the beginning, right? Like if we talk about the galactic plane. So with these new observatories, what do you expect for the galactic plane? Do you think are going to be able to just see some diffuse emission, or we'll be able to see something a little more defined that later can be picked on X-rays?
Yeah, that's a great question. To be honest, I think the neutrino field has not really thought very carefully about this problem. Let's say like the galactic plane was only recently discovered, and searches for individual sources are still in their infancy. So my personal opinion is this is very much worth pursuing. I work on an infrared telescope. We think that's really the best way to find transients, things like novae, for example, in the galactic plane. I guess it depends where it is in the plane, how many X-rays you could actually get out. I don't have off the top of my head a good number for what fraction of XYZ population you could see with AXIS within the plane. But if it's there, then obviously we should point AXIS to it and see. Yeah, I think this is going to be more important as time goes on because there's many new observatories which will see the galactic plane much better than IceCube. So yeah, it's definitely an area of focus.
Yeah, thanks, Robert.
All right, let's thank Robert one more time. So next we have Tingting Liu, talking about time domain and multi-messenger studies of supermassive black hole binaries.
So I'll continue the theme of multi-messenger astrophysics and tell you about, but here my messenger is gravitational waves. And more specifically, I'll tell you about the kind of T-time science we can do with supermassive black hole binaries and what kind of role AXIS will play in all of that. So we know that supermassive black hole binaries should form in galaxy mergers. When these systems are separated by a kiloparsec or so, we can directly resolve them as dual AGN. And we heard from Mike early this morning how AXIS will be able to find more of these systems at ultra high redshifts. But my talk will be focused on supermassive black hole binaries at milliparsec to centiparsec separations. This is where we cannot resolve the system directly spatially, but they are very interesting in this area of gravitational wave astronomy because they are strong sources of low frequency gravitational waves for pulsar timing arrays and LISA. And in fact, the Astro 2020 decadal survey mentioned that just like how the first radio telescopes and the X-ray telescopes opened up other parts of the EM spectrum, pulsar timing and LISA will open up other parts of the gravitational wave spectrum and reveal new sources and new surprises. And in fact, in 2023, pulsar timing arrays did open part of the gravitational wave spectrum. And here you're looking at the and PTAs do so by measuring through precision timing of millisecond radio pulsars. So the blue points here are measurements from the correlation of that gravitational wave signal as a function of the angular separation between the pairs of pulsars. And the black curve is the prediction, the so-called Henningsen-Downs correlation. And you see that the data follow the prediction very nicely. At this point, we cannot confirm the origin of this gravitational wave, nanohertz gravitational wave background. But looking at the amplitude and the spectral index of the background, the possible signal is consistent with the expectations of a population of binary black holes. So in the next few years to decades, as we get more data and more sensitive data, we can better constrain this background and perhaps confirm the origin of this signal. And in the next few years to decades, the pulsar time array experiments will get a major upgrade. And in the US, that major upgrade will come from the DSA 2000 array, where it will be able to time something like 150 millisecond pulsars at a monthly cadence. And at the millihertz gravitational wave range, that will be probed by the LISA mission coming up online in the mid-2030s, which will detect supermassive black hole binary, massive black hole binaries at the in-spiral and merger stage. So the remaining of my talk will focus on how what kind of role AXIS will play in the middle of that. So as I mentioned, these kind of supermassive black hole binaries cannot be spatially resolved, but we can understand how accretion works in these kind of systems using numerical simulations. And here you're seeing a snapshot from one of those simulations. We see this circumbinary binary disk, which acts like the gas reservoir, and gas flows onto the binary through these pair of strings that feeds the mini disks around the individual black holes. And these mini disks act very much like the standard aging disk that we're familiar with. So we can, and from these kind of numeric simulations, there are mainly two types of predicted EM persistent EM signals. One is to look for variability signatures, perhaps some kind of periodicity that's modulated on the binary orbital period. And the second type is to look for this kind of predicted binary disk accretion structure. For example, to look for the circumbinary disk or the streams or the cavity or these mini disks. So if these mini disks behave very much like standard AGN disks, we might expect each one will produce broad I and K alpha emission. And if you have two of these disks, you could see the two I and K alpha lines offset in energy, and they will oscillate as you see in the bulk motion, line of sight motion of the black holes. So a few years ago, it was suggested that in this source, there's a possible double-peaked ion K alpha line that could be consistent with this binary picture. So what we did was to follow up this source with more sensitive observations. So this work is being led by Yash, who you met this morning. But here we did a spectral analysis of this source at two epochs separated by about 6 months, and look for one, whether there's a double I line, and two, whether the lines oscillate in a way that's consistent with the binary hypothesis. So this is something we can do in the future with something like AXIS. And one thing I should mention is that this kind of signature is, you expect this signature in PTA binaries. So they are widely separated with year-long periods. So that's a more or less direct signature of binary mini disk accretion at the sort of 6 keV range. But there's a more subtle signature of mini disk accretion that appears at the soft energy range, and that has to do with the preferential accretion onto the mini disks. So the plot on the left shows the accretion ratio, M2 dot versus M1 dot, as a function of mass ratio, M2 versus M1. And the red points are from simulations, simulating accreting binaries with different mass ratios. So at 1-to-1 mass ratio, the accretion ratio is 1, as you might expect. But as you go to lower mass ratios, the accretion is preferentially onto the secondary black hole, the less massive companion. So that you can also see that on the figure on the right. So you have a smaller but brighter accretion mini disk around the secondary black hole. So the effect of that is that the different accretion rate onto the mini disk will change the ionization states of these two mini disks, the primary versus the secondary. And the total observed spectrum is the sum of these two. So you might expect this kind of effect will show up somewhere in the spectrum. So here in the geo case that we submitted, we look at, so these three panels are the residuals of the spectral fitting performed at three binary phases. And you see at the soft energy range below just 1 keV, where AXIS is very sensitive, you have these excess features that point to mini disk accretion. So in the last few minutes, I will talk about the synergies between AXIS and the LISA, which will observe massive black hole binaries at the in-spiral stage and the merger stage. And here, this is a prediction of the luminosity of the merging binary a few orbits or a few tens of orbits before merger. And the different colors are measured luminosities within some radius. So the dark blue tracks the mini disks, which are at the innermost radii. So you see that just before merger, the X-ray luminosity will gradually decrease as the mini disks begin to disappear. And in some fraction of the time, LISA can localize these systems within about 1 square degree. So it's possible to do short observations to tie that region to look for this pre-merger signal. And at the time of merger, LISA can localize the merger within about 0.1 square degrees. And that's an excellent match to the large field of view of AXIS. So we can point at that sky region and look for the post-merger rebrightening of this system. So just to summarize, in the 2030s, we will have 2 major gravitational wave observatories. We'll have PTAs operating at the nanohertz range and LISA at the millihertz range. And they will both be sensitive to, they will both probe massive black hole binaries in gravitational waves. And AXIS will be right in the middle of the action. And it can probe the X-ray signatures of accreting mini disks and also the merger signals of massive black hole binaries. And just a final advertisement, the AGN working group now has a time domain sub-working group led by Michaela Milagro and myself. So this QR code will take you to the Google form. So you have more science ideas that we perhaps missed. We would love to hear from you. And that's all. Thank you.
Right. Questions? So we.
Hi, Tingting. Can you tell us the time scale of that brightening post-merger? I'm just wondering, Chris has been asking about the response time, if we could actually catch that rise with AXIS.
Right. So these are right. So first of all, the time scale is short. It happens. You have so. Let me back up. About a decade ago, so people thought the binary would just merge in vacuum, and the disk could not. The so-called decoupling, the binary will inspire so fast, and then the disk left behind. So at the time of merger, there's no gas around to reignite the binary. But now we think that's not the case, and we think the system will rebrighten on a relatively short time scale.
So like seconds, minutes, hours?
More like hours and days.
Okay, so that's something we could potentially respond quickly enough. Okay, thanks.
Hi, very nice talk, very interesting work. I was curious, right? During the early sort of in-spiral stage, isn't the secondary experiences a higher burst of accretion? So is that also going to be detectable? What kind of, or does that depend too much on the parameters of the mass ratio and during the in-spiral phase, before you form these mini disks? Prior to that, you have a primary, and if you model the secondary plowing through the what's going to become the circumbinary disk, you expect that the secondary, there'll be a boost in emission around the secondary because of angular momentum loss right around there, suppressed accretion on the primary and a boost on the secondary. Have you looked at whether that's going to be a detectable signal too? Because that's a bit earlier.
Yeah, I don't think there's a lot of work on looking at the primary and secondary separately. Yeah.
So looking at them after they are quite close in and there's a circumbinary and two.
I also had a question on the timescale. So for like the typical mass mergers that Lisa will see, like how long before merger will Lisa have detected this? And we may not even really need to trigger. We'll just know exactly when to point our telescope to catch the decline and the rise. Yeah.
Yeah. So. Yeah. So I don't have the time scale in terms of physical time scales off the top of my head.
Yeah.
Yeah. But
okay. Yeah. Yeah, I don't think in M time either.
Yeah, there would be plenty of time. Yeah.
Yeah. Yes.
Yeah, this is really interesting. One of the slides had to do with the different ionization states for the disks. So I don't know if I didn't look at the spectra carefully enough, but is that something you could actually disentangle with AXIS, or do you need higher spectral resolution to pick out the different ionization states?
Oh, this is an AXIS simulation. So this is like 100 kilosecond. So
right.
you don't need to have super high energy resolution.
So you can actually like when you model the spectra, for example, you can pick out the two different ionization parameters or something.
So
like
you can. I see what you're saying. I don't think you can work out the individual ionization parameters, but you will see something is off in your spectrum. So if you just take the binary spectrum and just naively fit to a single agent, there will be unexplained access at this range that tells you something's off.
Okay, thank you.
I'll just comment on that point. There's probably going to be some degeneracy between detecting a 6.4 and 6.7 iron lines because different ionizations and the fact that you have a double peak line because of the 2 mini disks, right? So it's a complicated model at the end of the day, I suppose. Any other questions? If not, let's give a hand to Tingting. And we have the last talk of the session by Will Brandt, talking about galactic correlates of supermassive black hole growth and their application to AXIS.
Do I load it up here, or does someone load it up for me? I'm happy to do it if needed, but okay.
You want presenter mode or either?
That works for me. This is good. Great. Okay, thanks. So today I would like to review briefly some observational work my group has done on the galactic correlates of supermassive black hole growth over most of cosmic time. And I will also focus on an interesting application of them, using them as tools to model the growth of the overall supermassive black hole population, which has relevance to AXIS, as I will discuss. For example, it has relevance to this issue of the relative growth of supermassive black holes via accretion versus supermassive black hole mergers. A large team of us have been doing this work. I particularly want to highlight the work of some superb Penn State graduate students that I've worked with in recent years, and as well as postdoctoral researchers. And today, then, I will again focus on these galactic correlates. So to determine what properties of a galaxy really matter for supermassive black hole growth, Well, given the complexities of galaxies, one needs large statistical samples of well-characterized galaxies. And that's what we are getting from the cosmic surveys that we utilize for this work. I won't go and decode all of this table, all the details of this table, but briefly, we're using the best studied X-ray and multi-wavelength surveys for this work, now reaching a very large sample size of about 8,000 AGNs within 1.3 million galaxies that have all been systematically analyzed in a uniform way. Very briefly, then we analyze, we obtain the long-term supermassive black hole growth from the X-ray data by averaging over samples. And here we're using a combination of deep surveys, for example, the Chandra Deep Fields, as well as medium depth surveys such as XMM-SURVS, which targets the Rubin LSST deep drilling fields. And we're very excited in just a couple months when Rubin will begin operations to combine these X-ray data with the Rubin data, as well as then wide field surveys, for example, from eROSITA in the EFEDS field. And we utilize all of these surveys together to capture supermassive black hole growth in the most complete way possible. So then to obtain the galaxy properties, well, there we utilize the extensive multi-wavelength data that have been gathered in these fields by performing, for example, X-ray to far infrared fitting of spectral energy distributions using data from a number of superb facilities shown here. And we've systematically analyzed all these data, extracted SEDs, and fit them all in a systematically complete way, so we have sort of consistent results across large numbers of objects. And then finally, to look at the correlates of supermassive black hole growth, where there we perform non-parametric partial correlation analyses to determine which correlations are truly fundamental versus which ones are just secondarily induced. And there's a lot of work that has gone into this. I won't be able to go through all the correlation studies given the time I have, but briefly, we find that there are important correlations between supermassive black hole growth and galaxy stellar mass, as well as star formation rate, particularly of the bulge component, as well as galaxy compactness, as well as, well, and so those are the main drivers. And then we've also have looked at other possible drivers. We looked at sort of local sub-megaparsec environment as well as global environment. We find actually rather little effects from those to our best abilities to sample them right now. Again, I won't be able to go through all the details of this, but there are some review articles and a YouTube video that goes into this in much more detail. The one thing which I do want to highlight is this one here, this correlation with stellar mass. This is one that will be relevant to the AXIS application that I'll be discussing. So for the general galaxy population, just taken as a whole, spanning a very broad range of redshift from the local universe all the way up to redshift 4, long-term supermassive black hole growth seems to correlate most strongly with galaxy stellar mass. And you can see the correlation that's plotted there. It's a strong effect. It spans like 3 orders of magnitude in average black hole accretion rate as you go across that range of galaxy stellar mass. And you can see this applies at all redshifts, but I also want to highlight the redshift dependence there, such that you get more bang for your buck in terms of supermassive black hole growth as you move toward higher and higher redshifts. I will also mention just in passing that we have also tightly constrained the underlying conditional probability distributions that generate these types of results. This basically, these encode a tremendous amount of information about black hole growth as a function of galaxy stellar mass and redshift, and we've constrained these much more tightly than ever before. And then, well, how does AXIS come in? Well, obviously, first of all, AXIS could be used to extend these types of correlation studies with much improved samples. One could envision taking the superb AXIS data, linking them up to data from Rubin, from Roman, from JWST, from powerful wide field spectrographs and so on, for example, or narrow field spectrographs on the ELTs, and sort of advance this type of work in general. We've had a pretty good bash at it already, but there's still a lot that could be done there. But then, perhaps more importantly, more relevant today, is the applications of this work to AXIS. So we have recently published this paper, which I think has a number of relevant implications for aspects of AXIS. In particular, what we do in this work is we do a sort of hybrid approach to evolve the supermassive black hole population. The basic idea here is that observations, the ones that I've described, do a pretty good job now constraining the accretion channel, but they do not yet constrain very well the merger channel. On the other hand, simulations provide a reasonable merger channel, admittedly with still some uncertainties, but a reasonable merger channel, but a totally unreliable accretion channel due to the subgrid physics that is not able to be modeled very well. So we basically take the best of both worlds. We take the observations of the accretion, the simulations of the mergers, and we fuse them together. What we essentially do is we take this strong correlation that I've described, and we basically use that to regrow the black holes within a lustrous TNG. Following their standard merger tree and everything, they do a successful job tracking the galaxy population. We think they do a much less successful job tracking the supermassive black hole population, so we hack that in with the observations. That's what we're essentially doing. Briefly, what we're doing is we're iteratively solving this little equation over and over and over again to grow the supermassive black holes. There are many technical details here, which I won't have time to go into, but briefly, we have these two terms, an accretion-driven term, which we get from the observations, and a merger-driven term, which we get from the simulations. And when treating the merger-driven growth, here what we're doing is we track the most massive black hole along the entire merger tree, the one that ends up as most massive, and we treat lower mass black holes as being added to that more massive black hole as the growth due to mergers. So that's what I'm speaking of when I speak of growth due to mergers. Now then, what can we get out of this? Well, we can very nicely get a buildup of the supermassive black hole mass function, capturing again both accretion and mergers. This is what our best estimate looks like, shown here. You can see, as expected, there's rapid growth going from 4 to 3 to 2 to 1, and then essentially things freeze out at about a redshift of 1 over a very wide range of black hole mass, and essentially freeze out there down to the present day. We can also very nicely track where is the supermassive black hole mass as a function of redshift. These are our predictions for that, and we are now actually excited about taking these results and comparing them with direct measurements of supermassive black hole mass. Now, due to, for example, the Sloan Digital Sky Survey Reverberation Mapping Project, we have a big breakthrough in terms of having large numbers of reliably measured supermassive black hole masses out in the high redshift universe. We can take those and essentially use them to lock these results, provided you can work out the selection function, which we're working on presently. Okay, so then going to the key relevance to AXIS. Well, this plot here shows our average growth from accretion and mergers. The growth due to mergers is as I described previously, as I defined previously. We show the expected growth due to mergers using a nominal merger rate, where when a pair of galaxies merges, you have to work out the probability the supermassive black holes ultimately end up merging, as opposed to ending up as long-lived wanderers, okay? And then we also work out in sort of hard upper limit, where we essentially allow every pair of galaxies that merge to allow their supermassive black holes to merge. So you have a hard upper limit there. And you can see that, well, accretion is pretty clearly the dominant form of supermassive black hole growth over cosmic time. However, as we know well, accretion drops off going to low redshift, and it drops off considerably more sharply than the mergers do. And so the contribution due to mergers grows in fractional importance as you go down to low redshift, and you can see the quantitative results there. But even at redshift 0, according to our best estimate, they likely only contributed about the 30% level. Now, this is due to, of course, just the growth due to the supermassive black holes merging themselves. You may, of course, get enhanced accretion when galaxies merge together as well. But here, what we're showing is the growth due to the actual black hole mergers themselves. With a sort of proper model of separation versus time, one could actually take our sort of mechanisms that we have already developed and actually do predictions of, binary supermassive black holes as a function of separation, as a function of galaxy stellar mass, as a function of redshift, and so on. So that's an interesting thing to think about for the future. We can, for example, also break things down already as a function of galaxy stellar mass. This plot here shows, as a function of galaxy stellar mass, the relative importance of accretion versus mergers as you go down in redshift. And you can see the fractional importance of mergers becomes larger as you go to higher galaxy stellar masses. So that's of course relevant for AXIS as well. And then finally, we also, as a byproduct of what we do, generate predictions for the long-lived wandering supermassive black hole population. These are our predictions for that. Overall, at a redshift of 0, we get about sort of 23% of the overall supermassive black hole mass in long-lived wanderers. The mass fractions are broadly consistent with those derived by other authors as well, of course. And there are, of course, residual challenges in dealing with the wanderers due to the fact that you have large numbers of low mass black holes that end up as wanderers, and well, treating those is much more difficult. But in any case, if some of these wanderers can also support accretion activity, this will cause confusion, or alternatively will be an interesting additional signal of black hole growth, in sort of dual AGN. So that's worth considering as well. So I will be wrapping up there. I suspect I'm getting pretty tight on my time. And I will also just mention that other byproducts of this work, and we calculate the relation between black hole mass and galaxy stellar mass, as well as its expected scatter. And there's interesting predictions there. You can read the paper for details of that. We can also take individual supermassive black holes of interest and put them into context. For example, it appears that our galaxy's supermassive black hole is a bit of a slacker. Our galaxy's been underperforming in terms of generating supermassive black holes compared to other galaxies of its type. Interesting possible reasons for that. And I will end there, and I'm happy to take any questions. Thanks.
Nico?
Thanks, Neil. There is a paper from Pacucci and Loeb 2020 where they showed that the ratio between accretion and merger rates in the growth of black holes is also a function of not only of redshift, but also of the black hole mass.
Yeah, correct. Yep, correct. That is correct. And so I showed one, so we can take the results from our computations and break them down in a number of ways. For example, here I chose to show our results broken down as a function of galaxy stellar mass. In the paper, we have another plot like this, also as a function of black hole mass. Pacucci and Loeb did it one way. I personally think our results are perhaps more reliable because we're basically resting upon the giant computations of illustrious TNG and just building in the black hole growth on top of that. So there's a variety of ways to attack this problem. It's a challenging problem. You can read the technical details of the approach we took. We actually make comparisons with that paper in this work. So you can read the paper for the details.
Okay, thanks.
Yep.
Asha?
So that will likely be a layman's person question. What do you mean by wandering black holes?
Right. So yeah, sorry. Yeah, I went through that a little quickly. So this has been extensively studied in the literature already. So the idea here is when you have a pair of galaxies merging together, the supermassive black holes don't always end up merging. Some significant fraction of the time, you'll end up with a long-lived wandering supermassive black hole. And that can be actually a quite large fraction of the time. Just briefly, and again, I don't want to get too in the weeds here, but briefly, this shows estimates of the merger probability. Okay, and you can see that for certain, and Q there is the ratio of the two black hole masses, and you can see that for for a fairly wide range of that quantity, the merger fraction is low. It's like 20% or something like that. So you end up with a significant fraction of the time, the black holes don't merge, you end up with a long-lived wandering supermassive black hole in a galaxy. And people have investigated these already extensively. We've done it as well with our approach, and we get pretty good consistency with what other people have found in that regard.
So that would be based on your simulations, your calculations, assuming p-merge rather than a direct output from TNG, right? Because they
that's correct. Yes,
black hole positioning and instantaneous mergers, and yeah.
And there's a good reason why we do that. In fact, it's shown in this plot. I mean, to follow up on that, so this plot here shows our measurements of what we think the supermassive black hole mass growth is due to accretion as a function of galaxy stellar mass. And then it shows in the solid lines what illustrious DNG says it is. And you can see there are disagreements in both directions by like order of magnitude level. And this is not surprising. The subgrid physics in illustrious TNG is very simplistic. They basically just do Bondi-Hoyle accretion with an Eddington limiter and a couple of hacked-in prescription feedbacks. It's not so surprising it doesn't work very well. It's not so surprising it doesn't agree with observations. So we try to bypass the subgrid physics and just hack it in based upon the observations. We could do a better job in future work, but this is, I think, a pretty good way to do it, at least as a start.
Awesome, thank you.
Yep.
When you do these calculations, are there any hints about the fraction of mass that might occur in very obscured modes that are not detected by the observations, or is that totally degenerate?
That's a very good question. We've obviously thought about that quite a bit. I have a fairly long history doing X-ray astronomy. So yeah, we certainly have thought about that. There's several things that could be said there that they are covered in detail in the paper. So a few things. First of all, where most of the black hole growth occurs, it's at high redshift, where we're sampling quite hard X-rays. So we have good sensitivity to obscured systems to begin with. So that helps a lot right there, just straight out of the gate. In addition to that, we have looked at how much black hole accretion might be missed. There's a number of ways to do that. We have, for example, as I mentioned, done detailed spectral energy distribution fitting, running all the way from the far infrared through to the X-rays. That lets us identify AGNs that you might miss just from the X-ray selection approach alone. We've utilized that as well. We've also utilized other methods for AGN selection, infrared-based selection, radio-based selection, and so on. And what we find is about what you would expect from previously published works, both in the local universe as well as in the high redshift universe. You look at Wade's paper back from 2014, for example. It appears that you're probably missing sort of 30% of the accretion power. So it matters. We want to get it as right as possible, but we don't have any reason to think that it's so catastrophic that it's going to radically change the results. So that's briefly what I can say on that matter. There's a whole lot more that I could say, but I might wear out my welcome. So I'll stop.
Great, thanks.
Yeah.
Let's go with the standing microphone and then Priya.
Thank you for the talk.
Oh,
yeah.
Hi.
I have two small questions.
Yeah, sure.
One, you said that the strongest correlation was with galaxy stellar mass.
For the general galaxy population, that is correct.
Okay. And so how far behind in terms of correlation strength is the star formation rate, and are these galaxies on the star formation?
Yeah, you're warming me up here. Okay, I could go on forever about this. Okay, so yeah, I have all the plots. So, I mean, briefly, if you want to really know, okay, there's a lot of interesting things. The star formation rate does correlate in interesting ways, but it's primarily the star formation rate of the bulge that correlates. The star formation rate of the bulge correlates quite well, and essentially it correlates in a nice way such that the time derivative of the local universe relation between black hole mass and bulge mass agrees rather well with what we actually observe in the differential form of that relation in the high redshift universe. In other words, you take what we find in the high redshift universe, you integrate it up, and quantitatively you actually reproduce this pretty well. So we actually think we're seeing that information, in the process of information. So that is another non-trivial correlation that survives partial correlation torture testing against stellar mass. So that's one part of the answer. In addition, we've looked at other quantities. We've looked at galaxy compactness. That is sort of how centrally concentrated a galaxy is. There are non-trivial correlations there that also survive the partial correlation torture testing against galaxy stellar mass. This is led by Qingling Ni, a very good Penn State graduate student. You can read those results if you're interested. Also, then you can look at environment. Okay, environment does not survive the torture testing. Essentially, we had, for example, environment fight it out against galaxy stellar mass. Galaxy stellar mass totally obliterates environment by like 14 sigma, and so we see no real dependence upon environment once you control for galaxy stellar mass. And this is work by Guang Yang, so you can read about that as well. So that is a very short answer to what's covered in about 5 papers, but that gives you some of the key ideas. Is that answering your question to start with?
Yeah. And so are these galaxies on the star forming main sequence, or
which ones are you referring to?
The general population?
Yeah. Okay. For the general population, you're interested in the correlation with galaxy stellar mass. This is found both for the star forming main sequence and for galaxies off the star forming main sequence. We break it down in different star formation rate classes in the most recent paper by Zhao et al. 2024.
I see.
Okay. So it's there in general. And I mean, getting a little techie on that aspect, what happens is the functional form of the underlying generator function, the underlying conditional probability distributions, the shape of that changes, but the basic relation still remains.
I see.
It's there in a fundamental way, although the underlying shape of the generator function changes a bit. But it's just integration in the end. You just do the integral and it just pops this out.
I see. Thank you.
Great conversation for the coffee break,
okay,
which is starting right now.
Yep.
Thank you to the speaker and everyone in the